Okay, today we do Newton's second law, which I say is an algorithm for solving problems. So Newton's second law is probably the most important thing that you learn in this semester. We'll be using it over the course of the next couple of weeks. It sort of implies everything that we're going to do for the rest of the semester, but you'll also even use it in the next semester. So when you take Physics 221 and you look at problems of electromagnetism, electric force, you'll be doing problems with Newton's second law. So it's really important to understand how to do Newton's second law. And one thing I want to try and emphasize here is that it's really just a method. So I'm going to present you with what I call an algorithm for how to solve a Newton's second law problem. And the idea of an algorithm is that it's sort of a machine. You know how the machine works, and you turn the crank, and you get the result out. A lot of the problems that students have in solving Newton's second law problems that I myself had for many years when I was learning physics as an undergraduate, are that you try to think too much. So Newton's second law is a very precise equation, a very precise statement, and as I'll show you, basically the analysis of it is a math problem using vector math that we've figured out how to use over the past few weeks. So I'll show you exactly how to use that algorithm, and we'll basically apply it in exactly the same way for every single problem. And then when answering questions that are asked in the problems, you basically just use the results of that algorithm. So I'll show you what that means today. First, we'll talk a little bit about some types of forces. We introduced most of them in the previous lecture when we were doing our first examples of Newton's second law. Then we'll write down the free body diagram for an example or two. The free body diagram is the key object in Newton's second law, and so we need to know how to write it down. And it's also important to see how the free body diagram forces can be understood in terms of Newton's third law, which talks about the forces between different objects. So a free body diagram is for one object, but if you have multiple objects, then you should start to see Newton's third law pairs. We'll do an example to see that. Then I'll do an example in order to present the algorithm for doing Newton's second law, and I'll sort of walk you carefully through that, sort of identifying each step in the algorithm. And then we'll do two more examples using that algorithm to solve a couple of problems. So first, types of forces. And the reason we need to talk about this briefly is because the main thing that we do in a Newton's second law problem is write down or draw the free body diagram, meaning the set of all the forces acting on the object. So maybe you have I don't know, maybe you have some person that's like scaling a building here, and they're hanging onto a rope, something like that. So what does the free body diagram of the person look like? Well, in order to do the problem, you need to identify each force that is acting on the person. And as we'll see later, once you've done that, once you've drawn the correct free body diagram, then everything follows almost completely mathematically. That's why we call it an algorithm. So if you can get the free body diagram correct and you know how to do the algorithm, then you'll be able to solve all of the problems. If you make a mistake in the free body diagram, then that means you've made a mistake in the physics, and the answers that you get in the end won't be correct. So it's important that we know what kinds of forces exist, when they exist, what their magnitudes are and how they point, and then we'll be able to sort of look at an object when drawing its free body diagram and say, okay, does this force apply to the object? Does this force apply? And we'll know the rules for it. So just as an example, here's this person. We'll go through a couple of forces in a second, but if we make a free body diagram for the person, so here's their dot. Well, what do we see? We see that there's a rope that the person is holding on to. So we say that there's a tension force that points along the rope. We know that the person has mass, so that means that there's going to be a force of gravity down to the center of the earth on them. And then we see that their foot is touching the wall. So you see that there's a surface of contact here between the person and the wall. And therefore, well, there might be a couple of forces. We know that there's going to be a so-called normal force perpendicular to that surface of contact. There might also be a frictional force, and usually that's parallel to the surface of contact. So let's just draw one. So maybe there's a force of friction pointing up. We don't necessarily know that, and we're going to cover friction in the next lecture. But that's an example of how we draw a Newton's second law free body diagram. And you notice as I was doing it, I was sort of going through forces in my head, asking whether they existed or not. Maybe you couldn't tell that because I was doing it in my head, but that's the process. So let's talk about the forces that we know about. So one is the gravitational force. So it acts on any object with mass. So we know that if you just have an object, so let's say, I don't know, what can we do? Let's say that there's like a roller coaster, just to make it interesting, and the roller coaster is upside down on the track. Here's all the people. I don't know if that's their hair or their arms. So regardless of anything else that's going on in this problem, we know that the roller coaster itself has mass. And therefore, when we draw its free body diagram, we say, okay, there is a force of gravity, and that force of gravity points down toward the center of the Earth on that object. So to specify that force, we say Fg has a magnitude of mg. We found that in the last lecture. And Fg vector points down. And down means towards the center of the Earth. Okay, another force that we mentioned in the last lecture was the normal force. So whenever you have objects in contact, so whenever, oops, I don't know how I'm spelling whenever an object is in contact, geez, it's really rough for me spelling today, contact with another, there is a normal force. So, I don't know, maybe, let's say somebody's just sort of leaning up against a wall, like that. So you can see here that there's actually two places where the object, meaning the person, make contact with another object. So their feet are making contact with the floor and their back is making contact with the wall. So we might draw those as two normal forces, so like Fn wall and Fn floor. And you notice how I drew them. So Fn points perpendicular to the surface of contact. So I've been drawing this surface of contact with like a green flat line, and the perpendicular actually has a synonym, which is normal in math. So when we say a normal force, what we mean is that we mean a perpendicular force to the surface of contact. I guess I should also say that a priori, if we don't know anything else, the magnitude of Fn is unknown. So there's no equation for the magnitude of a normal force. We'll find the magnitude of a normal force by applying Newton's second law, and comparing it to the action of other forces. Okay, a tension force exists whenever you have a rope or a string acting on an object. So let's just write that down. Tension force whenever a rope, string, wire, acts on an object. So let's draw that. Let's say that we have a child on a swing set, maybe. So we have a swing set here, and the child is going high. So there's a chain here, and it connects to the swing. Maybe the child dropped off. Now I don't have to deal with the child. So we have a tension force acting on the swing itself. So we have a wire or a rope or a chain or something here, and we say that there's a force of tension on that swing that's at the bottom of the wire. And so what do we see? We see that the force of tension points along the rope. Again, I'm not able to actually spell words. Along the rope. And there's one other thing that we should say here, and you see this when you have multiple objects connected by a rope or a wire or a string. So for example, if I have like, say a block that's sitting on a table, but it's connected across a wire through a frictionless pulley to a block which is hanging from off of the side of the table. So maybe these two objects are accelerating. So we have A1 is going across the table and A2 is going down. It turns out, well, we can see that there's going to be a tension force on both objects. So there's going to be a tension force 1 on the one object, and then there's going to be a tension force 2. Sorry, let me draw that off to the side here. Force tension 2 acting on the second object. And notice that I drew them exactly as I stated here. The force of tension acts on an object along the rope. There's another rule here about tension forces, which is for light ropes, and we should say across frictionless pulleys and massless pulleys, the tension is constant. Maybe I should say uniform, meaning that it's the same at every place in the rope. Constant usually means constant in time. What I mean is that the value of the magnitude of the tension is the same all the way along the rope. So in addition to writing down these two forces, at some point I can make the expression that the force of tension 1 magnitude, let me draw it off to the bottom, the force of tension 1 is equal to the force of tension 2 in magnitudes, and we might just give that a name and call it the tension in the string. Something like that. So this is an additional rule for tensions, which we haven't seen yet, which says that if you have a rope that acts on multiple objects, then as long as you can be assured that the rope is light, which we will usually assume, in fact we'll probably always assume it, then the tension is the same at every point in that rope. In fact, it's the same magnitude pulling on each object. So even though we'll see problems like this, even though these two objects are sort of moving with and against their forces of tension, those magnitudes of those tensions are exactly the same value. So just one more force that I might mention is a push or a pull. So you might have a person that's sort of pushing on a box or something like that. So here they're pushing on a box, and so we could say that there's going to be a pushing force. It's perfectly fine to talk about pushing and pulling and applied forces. Usually those things will be of some other category. So in this particular case, the person's hands are up against the box, and that means that there's a surface of contact. So we could have called this a normal force of the person on the box. There's another normal force of the ground on the box, which would point upwards, but this pushing force is also called a normal force. And it's fine to call it a pushing force instead of a normal force in this case. But that's just another type of force that you might have acting. And the idea, remember, of all of these forces here is to have in mind what is the list of possible forces and sort of go through that list when you're looking at a free body diagram. I'm not sure what I wanted to say up here. So as we'll see, the construction of the free body diagram is the only physics in solving such a problem. All else follows from the vector math and algebra. And I guess therefore we must get the free body diagram right. So the way to get the free body diagram right is to have this list of possible forces in your head and to go through them and to know exactly the direction in which they act and the magnitude in which they act, with which they act. Okay, so this is a preliminary example just to draw out some free body diagrams before we actually use them in the context of Newton's second law. And I want to take this opportunity to talk about Newton's third law pairs again, just to show a few things about that. So we have a worker in a warehouse pushing on a 100-kilogram box, but that 100-kilogram box is pushed up against a 200-kilogram box behind it, and they're trying to move them back out of the way. So what do we have? We have like the floor of the warehouse, and then we have the worker leaning against the box, and we have like a small box. Maybe we'll call that MA. And then there's a second box, MB. There. And so we've drawn a picture, and now we want to draw a free body diagram for each object. So we could draw a free body diagram right on the picture. So we could consider the person an object. We could consider box A an object. We could consider box B an object. And we could just start drawing vectors on there. It's going to get a little bit complicated, so maybe we should instead use the way that the quote-unquote free body diagram is intended, which is to free the diagram from its body. So we'll just make 3 dots to represent the 3 objects. So this is the person, this is box A, and this is box B. So let's try and see what the forces are acting on them. So, and what we're going to do is we're going to try to give them unique names. So I don't want to say that I have a normal force acting on A and a normal force acting on B and call them both Fn, because then I'll have 2 different forces that I've given the same name to. So we need to try to make sure that we give unique names. And I'll probably use the A, the B, and the person identifiers to do that. So let's start with the person. So the Now let's start with box A. So for box A, well, we have this applied force of the person acting on the box. So we could call that like a pushing force. So F push, maybe F push on A. Let's call it FPA. Okay, so that's going to be the force, the horizontal force of the person pushing on box A. That's where it would appear on the picture. What else is acting on A? Well, box A is in contact with the ground, so there's a normal force of the ground pushing upward on box A. So I should put Fn A. There's a normal force upward. What else? Well, we're told that that box has mass, so therefore there must be a force of gravity acting on A, and I call it FGA. Anything else? Well, for now, maybe not. Let's move on. So how about box B? Well, it looks like box B is sort of also being pushed on, right? There's a surface of contact for box B, so I should show sort of the force of box A on box B, right? There must be a force of A on box B. Maybe that could be called a pushing force, but I'll just call it force of A on B. What else is acting on B? Well, there's going to be a force of gravity on B because it has mass. Probably should have drawn that longer than on A because we know that it has more mass. There's going to be a normal force on B. Is there anything else? Maybe not. So let's move on to our third object, the person. So we have a person, and that person has mass. So that means that there's going to be a force of gravity on the person. And though they are standing on the ground, so there's definitely going to be a normal force of the ground on the person. Is there anything else? Well, I don't know. Let's move on to the next step. So the next step, part B, says to redraw each free body diagram using Newton's third-like names. So remember, Newton's third law says that the force of object A on B is opposite to the force of object B on A. So Newton's third-like names means to give two objects within the force, and then the second one is the one that we act on. So if we're drawing a free body diagram, for example, for the person, then all the forces acting on the person should say on person. And then we'll use the other object that's acting on them. So let's start with that. So let's start with the person. So we have the normal force on the person. So what is that? Well, that's the normal force of the ground acting on the person. So we have force normal of the ground on person. I'm going to write it out sort of with that on there just to make things perfectly clear. Okay, and then the other force we had is the force of gravity of, well, what is acting on the person? Well, the force of gravity is the pull of the earth. So this is going to be the force of gravity of the earth on the person. So we've made it clear what are the objects that are acting and what are the objects that are being acted on. And you notice that for the free body diagram of the person, I have forces acting on the person only. Okay, let's look at the next one. So we have the pushing force, what do we call it? We called it the force of push on box A. That was this force right here. So that should be a force on box A, but it's a force being acted on by the person. So I guess I don't need to change the name too much. What kind of force is it? Well, the person is acting with, I guess, a normal force because their hands are pressed up against that box. So let's call it a normal force, force normal, of the person on A. So that's a better way of writing that rightward force that's acting on mass A. Then we have the downward gravitational force. So we have the force of gravity of Earth on box A. And we have a normal force, which is the force of the normal force of the ground on A. And again, you notice, you want to check this, each of those forces are acting on the object A, even though I've written the object that acts as well. Now let's move on to the last free body diagram. So we have the force of A on B. So that one basically already was a Newton's third law name. So all we might do is to say what kind of force it is. It's a normal force of A on B. Then we have gravity and normal, just like the other ones. Again, that should be a longer one, right? So force of gravity Earth on B. And then we have force of normal ground on B. There we go. So we've given Newton's third law names. Now, there's a couple other things that we should do. So one is Newton's second law is sort of represented by this free body diagram. And Newton's second law has the expression the sum of the forces, which we sometimes also call F net, is equal to the mass times the acceleration. So if we want that equation to be represented in the picture, then we really should also include the acceleration vector when we draw the free body diagrams. So I'm going to do that, and we sort of have to go back to the beginning and say, well, this person is pushing the boxes, so it's not clear exactly what's happening. I mean, the acceleration could be backwards, forwards, or zero, depending on what's happening. If it's a frictionless force, and I didn't include any forces of friction here, then it's likely that we'll have an acceleration forward. So let's assume that there's going to be an acceleration of box B in that direction, and then because the objects are connected together, there's going to be acceleration of all of the objects with exactly the same magnitude. So we might say AP is equal to AB is equal to AA. But I've included the acceleration, and then I should put that next to my free body diagram. So AP, AA, and AB. And one reason for doing that is because you might find that there are other forces that you've forgotten about. So it looks like these two free body diagrams are consistent with the acceleration, because if you imagine adding up these three forces, you'll just get something that points to the right, and that means that you'll get an acceleration pointing to the right. That's what Newton's second law says. So this looks okay. This one, the same thing. You have a net force, a sum of these vector forces that points to the right, and therefore you'll get an acceleration pointing to the right. But over here, if the person is accelerating along with those boxes, then there must be another force that I've left out. And so we should probably include, I guess, it's a force of friction on the person. So that would be the force of the floor allowing the person to go forward. So if it's a frictionless surface for the boxes, maybe they're wearing spiky shoes so that they can actually push on those boxes. So that shows us one force that was left out. Now Newton's third law also can show us forces that are left out. So remember, Newton's third law says that for every force, there's an action-reaction pair. So for example, I had over here the force of box A on box B. That means that if box A is acting on box B, there should be a force of B acting on A, and therefore I need to have a force over here, which is the Newton's third law pair. So there should be another force here, which is the force of normal of B on A. So notice two things. One is, again, it's a force on A, so it goes on a free body diagram for object A, and it is the Newton's third law pair to this. And you can see that exactly in the way that it's written. They're both normal forces, and then they have a reversed action, A on B, B on A. So are there any other forces that we've missed then? Well, there are. So I've put in a frictional force acting on the person. So that's the force, I guess, of friction of the ground on person. But if there's a force of the person acting on A, then there must be an opposite force of box A acting on the person. Force of A, oh sorry, it's a normal force of A on person. So that's one force that we've lost, that we left out. So now we can check. So let's look at the pairs. So we have the normal force of A on the person. Its pair is the normal force of the person on A. So if we were to draw that on the picture up here, those would be Fn A on person and Fn person on A. And you can see why I didn't try and draw all my forces up there. What else do we have? Well, we have the force of A on box B, but we also have the force of B on box A. It must be there. And I guess that's it for the third law pairs in the horizontal direction. Do I have any pairs in the vertical direction listed here? Well, it's a common mistake for students to say, well, I do have a pair. I have the normal force and the force of gravity. That's a Newton's third law pair. No, that's not true. So there's two reasons that that's not true. One is a Newton's third law pair must be the same type of force. So here it's a normal force and a gravitational force. And the other, probably more important reason, is that when you have a Newton's third law pair, they act on different objects. These two forces act on the same object. So each of these forces should have its own Newton's third law pair, and you can see what the other object is. So for the normal force, this is a force of the ground on the person. So then we would have to take an object which is the ground and say, okay, well, there must be an opposite force, a normal force of the person on the ground. Then we have the force of gravity, which is the earth on the person. Well, you might say ground and earth are the same thing, but what we mean is that the entire earth is pulling on the person downward. But by Newton's third law, and this might seem weird, the person is also pulling upward on the earth with exactly the same force. We're not going to cover that right now, but we're going to come back to it when we talk about so-called Newton's universal law of gravity. So the Newton's third law pair here does not appear anywhere on these diagrams, but if we were to draw a free body diagram of the entire Earth, then it would appear. Okay, so I think that that's all that I wanted to say about these Newton's third law pairs. You can see that it gets quite complicated, and there will be times when it's good to try and write out the forces explicitly like this, just to make sure that you've gotten all of them. So if you see a problem where you have a lot of interaction, you might want to write out forces with these kind of names so you can make sure that you haven't left anything out. You should certainly be thinking in mind, well, if I have one object pushing on another, then I must have the other object pushing on the one. You must have that third law pair. And then the last thing that I would say about it is something about adding up vectors and cancellation. When we do Newton's second law for the person, then these forces, all of these vector forces, will appear in a single vector equation, and you might be able to say something like, well, the normal force cancels with the force of gravity. That will never be true for a Newton's third law pair. So for example, the normal force of A on B would appear in Newton's second law for this object, object B, but its pair, the normal force, oh, it's over here, the normal force of B on A appears on a completely different object and therefore a completely different Newton's second law equation. So these Newton's third law pairs will never appear in the same equation. And we'll see that happening. Okay, let's look at Newton's second law. So what I'm going to do in this section is I'm going to take an example, and I'm going to use that example to show you what the algorithm is for doing a Newton's second law problem, or as I shorthand that, doing Newton 2. So doing Newton 2 is the process of taking a single object, maybe that's a box with mass, why would I call it A here? Let's just call it a box of mass m, making a free body diagram for that object. So maybe, I don't know, maybe it's a mass that's hanging from a rope, and therefore the free body diagram would look like the force of tension upward, the force of gravity downward, and maybe it is accelerating downward. So that would be what the free body diagram looks like. And then taking that free body diagram and making a Newton's second law equation out of it. So you can write that as the sum of the forces is equal to the mass times the acceleration, or you can write it as F net. But applied specifically to this problem, the sum of the forces is the literal sum of the force vectors. So we take an object, we make a free body diagram, and we translate that into a Newton's second law equation, and then we can do vector math on this process. So the process of doing Newton's second law will take us from free body diagram to equation, and then we'll do vector math to get numbers out of this. We'll translate the vectors into magnitudes, and we'll get some relationship between the magnitudes of all the vectors. Those resulting equations will be called the boxed equations, and it will be those boxed equations that you put together with some algebra to answer any questions that are asked in the problem. That's the process for one object. If you have multiple objects, then you just do Newton 2 for each object. So you imagine that there's multiple objects, and you would just have this exact process for each object, and we'll show how you do that. When you do that, you'll get more boxed equations, and then you put all the boxed equations together. And then finally, if you're asked questions, it's actually my suggestion that you just ignore the questions at first and simply do Newton 2, because anything that you're asked has to come out of those boxed equations that you get from Newton's second law. So there's almost no point in trying to answer any questions. In fact, I would say there is no point in trying to answer questions until you see what Newton's second law gives you for each object. And then it will be basically trivial. You'll have all of the information you need to answer any question. You'll just have to do a little bit of algebra. We'll see how that comes about. So let's take this example. We have a block of ice that's sliding down a frictionless roof, which is inclined at 30 degrees with respect to the horizontal. Find the magnitude of the acceleration and the normal force exerted on the block of ice. So, step 1, draw a picture. We know this from all of the other types of problems we've done. It's important to draw a picture first so you can sort of see what's going on. Whoa, I don't know what happened to that roof. So we have a roof here, and the roof is angled at 30 degrees. So I'm going to give a name to that. We'll call it theta. And then we have a block of ice, which is sliding down, and we'll give it a mass, give a name to that, which is mi. Could have just called it m, but let's call it mass of the ice. Anything else that we need to draw here? Well, we were only given the mass and the angle, so I guess that's enough for now to draw the picture. It's important to give names to things that you know, and also names to things that you don't know. We'll have some more in a second when we start to draw forces. So, for one object, and in this problem we only do have one object, carefully construct its free body diagram. So let's redraw that picture. I'll be drawing it multiple times here to give you a sense for what's going on along the way. So here's our object. I call it MI, and I want to draw the free body diagram for that object. So that means I need to go through the list of forces in my head and ask whether they exist. In addition to have the forces acting on the object, I want to also show the acceleration vector of the object. So hopefully there's some information in the problem that will allow me to know what that looks like. So free body diagram, I'm just going to put it directly on the object because I just have one, so it's pretty easy to do. And we go through the list of forces in our head. Well, the object has mass, so there's going to be a force of gravity acting on it. So I draw a force of gravity vector. What else? Well, there's no rope acting on it, so there's not going to be any tension forces. There's nothing pushing or pulling on it, so there's no push or pull forces. There's no friction. We didn't learn about friction yet. We'll do that next time, but there's not going to be any frictional forces. The ice is in contact with another object. So if you notice, there's a surface of contact here where it's touching the roof, and therefore there'll be a normal force along the perpendicular to that surface of contact. So if I just draw that perpendicular, then I'm going to have a normal force that points perpendicular. Keep going through the list of forces in my head. I think I've gone through just about all of them. I can't think of any other forces that are acting, so I guess those are all the forces that should be on my free body diagram. Remember, there's a second part to drawing a free body diagram, and that's the acceleration vector that we draw off to the side. So what I mean by that is to draw a vector for the acceleration, give it a name like A, and also draw it in the direction that we think it's going. And sometimes that's not obvious, but I think in this case it's fairly obvious. You can see that the sum of these forces is going to point somewhere toward the right, because those forces sort of point towards the right. Something about them canceling out and pointing towards the right. And the object is basically moving along a one-dimensional line. It's moving along the roof. So if the object's accelerating, then it should be that the object is going to be accelerating in this direction here. So I'm going to draw a vector for the acceleration that points along the roof like that. Okay, so that's my complete free body diagram. Now, we write down Newton's second law. So Newton's second law says the net force is equal to the mass times the acceleration, and we just write that down off of the equation sheet. So I'm going to first copy my picture down here, and then I write down Newton's second law. So F net is equal to the mass times the acceleration. That's what you see on the equation sheet. You're also welcome to write sum of the forces is equal to the mass times the acceleration. These two things, they mean exactly the same thing. F net is the sum of the forces. This sigma here means sum of the forces. So you could write that as well. I'm going to erase it here for now because I've already chosen one of those options. So I write down Newton's second law, and then I look at my free body diagram and I make this general law of nature specific to the problem that I have in this object, meaning I replace F net with the sum of the forces. So I have a normal force, and I have a gravity force. And then I have the acceleration of the object. That's it. Now, in fact, this is the end of the physics. So physics is given by a general law of nature. It says the sum of the forces equals the mass times the acceleration. We've applied that general law of nature to a carefully constructed free body diagram, and then we've written it out. So this is what Newton's second law tells us. It turns out that everything else we'll do from here on will be simply some math. We'll do vector math on this vector equation. And you've done that before in other contexts. We'll do it carefully here, but nothing that I'm doing below should be surprising to you because you've done that type of analysis before. So that's what I'm saying here is we're finished with the physics. The rest is just math. just is doing a lot of work in that sentence, I realize, but it's really true. So let's copy that and let us continue on. So in order to deal with a vector equation, what we're going to want to do is we're going to want to make an x equation and a y equation out of it. Remember, there were two things you could do with a vector equation. You could work with it graphically, or you could work with it algebraically by writing out components. Of course, x and y don't mean anything until I draw a coordinate system. So this step 4 is to simply draw a coordinate system. Now, remember, you're allowed to choose any coordinate system you want. You're allowed to work with an x and y in any directions that you want. In problems of Newton's second law, there are often some coordinate systems that are better than others. Not that they'll lead to a different answer, but just that they'll lead to simpler analysis. And the way that you choose a coordinate system is to try and get it to line up with as many vectors as possible. So if I were to choose just the normal xy that we usually do, and for problems of forces, it doesn't matter where I draw the coordinate system, I'm really just defining the positive x and the positive y directions. If I do this, well, you say, okay, that coordinate system is nice because it lines up exactly with the force of gravity vector. That's something we've been doing in free fall. However, if you look at the other forces, you say, oh, well, but I don't get it lining up with my normal force, and I don't get it lining up with my acceleration. Is there a better choice that I could make? Well, in this case, there is. And that choice is to align the x direction with the ramp. That way it will line up with the acceleration vector. And then the perpendicular to that, the y direction, lines up exactly with the normal force. Now you see I get a normal force along the y, and I get the acceleration along the x. The only thing that's not lined up with my axes is the force of gravity. So that will simplify my equations. However, you could have chosen any coordinate system you want. This is just sort of the simplest one that we can use. Okay, so let us move on. I'm going to copy this and we'll go to the next step. So the next step says, I'm going to erase this little piece because that's exactly what we're going to do. You want to rewrite your Newton's second law vector equation for either the x or the y direction. And what that means is just to replace the vector symbol with a component variable. So for example, you take the fg vector and you change it to fgx. So let's do that. So this vector equation is going to become an x equation. And then I guess I should just say later it will become also a y equation, but we'll leave that for a moment. So in the x equation, we have, we just rewrite exactly the same equation from Newton's second law, but we take off the vector signs and we put little x's. So we're saying fnx plus fgx is equal to max. So why is it that I'm doing that? Well, let me just remind you, the a vector means ax comma ay. The normal vector means fnx comma fny. And when you add those things together, you add the x's separately from the y's. So if something is true for a vector equation, like this, then it will also be true for the x components of each of those things. And that's exactly what I'm writing down. I'm just writing it down explicitly. So this is what you should have in your head, that I can break up each vector into components. The way that we write it down will just be by replacing the single equation, the single vector equation, with an equation for the components. I often say that this is a don't think step. Don't think, just write down. So don't think about what you're doing, just rewrite the vector equation as a component equation. Now we want to think. So the main part of this step is what's written here. Replace, oh no, I'm sorry. I've written it down here. We want to express each component in terms of the magnitude of that vector. So what do we mean by that? Well, you know what this symbol means. It says the Fnx, which is the x component of the normal force vector. So you also know how to find the components of a vector. You take the vector, you place it on a coordinate system. So let's just do it carefully. So I'll redraw my coordinate system, meaning I'll draw a coordinate system that is angled in exactly the same way. And then I'll place my normal force on the coordinate system. Now, to find the x component, I go to the tip of the vector and I go back to the x-axis. This is the x-axis here. And where do I land? Well, I land at 0. So we see that Fnx is equal to 0. In fact, we chose our coordinate system, so that would be true. Okay, that's one of them. Now we move on. Fgx. Well, I do exactly the same thing. I place my vector on the coordinate system. Here's Fg. And then I go from the tip of the vector back perpendicularly to the x-axis. And that's going to be what I call Fgx, this tick mark. So that one's a little bit harder to see, and I'm going to need to do a little bit of work to figure out what that actually is. So to find the component, I want to draw myself a little triangle. So I have this triangle here. It's going to be a right triangle because I went perpendicularly back to the axis. The hypotenuse is going to just be the magnitude of the force of gravity vector, and then I'm looking for this side, which I could just call x. Now, this is maybe one of the hardest things that we have to do, certainly in this unit, but maybe in the whole section of the course, which is to try to figure out which angle goes where. So I was given the angle of the ramp here, but I don't know exactly where that is inside of this triangle here. So there are a couple ways that you can see it. In my opinion, the easiest way to see it is to draw the horizontal on your coordinate system, meaning this here. So that line is the same as this line here. And the reason I've drawn it is so that I can say, well, I know that this angle here is theta. Okay? Now that angle is theta, but this angle is 90 degrees. So that means that this angle up here at the top is not theta. That angle is 90 minus theta. So going back to our triangle, this angle is 90 minus theta, which means that this angle is theta. So you might rewind the video and go back and repeat that argument for yourself, because you're going to want to figure out how to get the angle into your triangle here. Once you've done that, then it's a pretty simple analysis. We've done it before, so we see that x is opposite to that angle, so I write sine theta is equal to x over magnitude Fg, or x is equal to Fg sine theta. And then I remember, one last step. This is always a positive number because it's a length on a triangle. I need to check to make sure whether Fgx itself is positive or negative, but of course it is positive because it landed on the positive x-axis. So after all that, we found that Fgx can be replaced with Fg sine theta. Okay, now we're not done. The equation continues past the equal sign, so I have an m, that's not a vector, so I just write it down, and then I have ax. I need to find the x component of this vector. So what is it? Well, if I take that vector and I place it on a coordinate system, well, let me do it, even though I'm getting too much stuff here. So here's my x-axis and my y-axis, and I take my acceleration vector and place it on the axis. There it is. This component, ax, is a positive number, and it's exactly equal to the magnitude of the vector. So I see that a sub x is simply plus a. Notice these things are different. So we started out with a vector equation. We said, okay, if it's true for the vectors, then it's true for each component. So I replaced a vector with a sub x. Now, depending on the coordinate system I've chosen, a sub x could be positive, negative, 0. It could be a magnitude times sine theta or something. But in my analysis, by placing it onto this particular coordinate system, I find it's equal to the magnitude. So I've specified exactly what the ax variable is in terms of the magnitude of that vector. And I did the same thing for these two. The x component of the normal force turned out to be 0. The x component of the force of gravity, I've written in terms of positive quantities, the magnitude of the force of gravity and the angle that we were given. This is going to be our first boxed equation, so I'm just going to clean it up a little bit. I get magnitude Fg sine theta is equal to ma. And all of those are just positive constants, which we were either given or we might want to find. Okay, that's one equation. What's the next step? Well, the next step is to repeat step 5 for the other coordinate directions. So I think I still have, yeah, I do. So remember last time I went and got the x equation. So that's the last page, previous page. And now we're going to do the y equation. So what is the y equation? Well, remember this is the don't think step. I just rewrite my vector equation, but in terms of components. So if fn vector plus fg vector is equal to ma vector, then fny plus fgy is equal to may as well. Then we have sort of the meat of the whole process, which is to find these components in terms of magnitudes. Let's quickly draw our coordinate system again. And we take each vector, we place it on the coordinate system. So I have Fn points along the y direction, and it's along the positive y. So Fny is this number, which is a positive number. It's equal to the length of the vector. So I replace Fny with Fn magnitude. You could also write it like this, the magnitude of the normal force vector. Fgy, well, we found that already. We did most of the work to find it. We had looked at Fgx. Now we're looking at this number, Fgy, and we had our triangle. Let me copy that triangle here. Now I'm looking for this side, and so we have, that's the adjacent side to theta, so we have cosine of theta is equal to y over fg, or y is equal to fg cosine of theta. Now, if I go back and look at my coordinate system, though, I see that fgy is this tick mark, which sits on the negative y-axis. So fgy is a negative number, but its absolute value is this quantity here. So what do? I replace fgy with minus fg cosine theta. And then finally I go to the other side of the equation and I have may. Well, if I look at this vector on this coordinate system, you see it points only in the x direction. Its y component is 0. So you've got to make sure you do that, because that leads to a very nice equation where there's a 0 on one side. And finally, what do we get? If we tighten this up, we get Fn is equal to Fg cosine theta, and that is our second boxed equation. There we go. Okay, next step is if there are multiple objects, then you want to repeat each of those steps. So everything we just did for a single object, meaning free body diagram, Newton's second law, breaking up into components, doing each component separately and arriving at boxed equations, you need to repeat that for every single object. It might seem like a lot of work, but once you've done this a few times, it's not really work, it's just turning the crank of a machine. And you get to boxed equations, and the equations help you solve problems. So the last step is using all of your boxed equations and any force magnitude definition. So we know that, for example, the magnitude of the force of gravity can be written as mg. Then you answer the questions. So I'll just rewrite the two equations that I got. The first equation was Fg sine theta is equal to ma. And the second equation was Fn is equal to Fg cosine theta. Now, what were the questions that were asked of me? Remember, I've forgotten about them because I told you to forget about them. Just do Newton's second law and then come back and look. So we want to find the magnitude of the acceleration of the ice, that's what we called A, and the normal force, meaning the magnitude of the normal force. Well, it's asking for a force, so the direction is perpendicular to the roof. That's what we mean by normal. But the magnitude we can find, that's already this equation. So what is it? Magnitude Fn is equal to magnitude Fg, that's mg, times cosine of theta. So I've plugged in the expression for Fg. Now I just plug in the numbers. So let me go back and see what they are. 20 kilograms, and the angle is 30 degrees. So let's plug in those numbers to my calculator. So we have 20 kilograms times 9.8 meters per second squared times cosine of 30 gives me 170 approximately. What are the units for that quantity? Well, it's a force, so these are newtons. So the normal force is 170 newtons. By the way, the magnitude of the force of gravity is equal to mg. And what is that? Well, you can see because we're not multiplying by cosine theta, it'll be larger. So 20 times 9.8, the weight of this object, we call that the weight, is approximately it's exactly 196 newtons. So this is a case where the force of gravity is not equal in magnitude to the normal force, which we did see in some other examples before. And that's because they're at angles with respect to one another. So this is one of our answers. The other answer was the magnitude of the acceleration. So that's equation 1. So equation 1 tells us, well, A is equal to Fg sine theta divided by m. Doing a little bit of algebra. We can do even a little bit more algebra because Fg is mg, and we see that the mass actually cancels out in this equation so that the acceleration is just g sine theta. This is actually something Galileo did. If you remember, to see that objects all fell with the same acceleration, he didn't drop objects vertically, but he allowed things to sort of roll down an incline, and you can see that the same thing is true. The acceleration of an object going down the incline does not depend on its mass at all. We find that it's just g times the sine of the angle. So what is that? Well, let's plug that in. So we have 9.8 times sine of theta, 9.8 times sine of 30 degrees, and we get 4.9. And that's our second answer. So what I hope you see is that once you have the things that you got from doing Newton 2, it's very simple to answer any of the questions that are asked. In fact, it's the only way you'll be able to answer the questions that are asked. If you tried to do it up above before you had these boxed equations, before you did Newton 2, then it's likely you'd make a mistake, and you'd certainly confuse yourself because you don't have this solid logic of Newton 2 guiding your way. So we went through the algorithm. I gave you the steps to follow, and I'm going to do that every time. I'm certainly not going to write it out in this way with all of these words and explaining everything that I'm doing, but the process will be exactly the same every time I do a Newton's second law problem. And we'll do two examples now. So first example, we have two artifacts in a museum display that are hung from vertical walls by light wires. So we're supposed to find the tension in each wire. Well, okay, we're given a picture here, but we might want to redraw that picture for ourselves. So we have object A, which I'll call mass A. We were given the weight of it, and so we know that weight is equal to mg, so that means that mass A is equal to the weight over g, if we ever need to know that. So this is going to be the weight divided by g. And then hanging, and that thing is hanging at an angle here. We were given this angle here, so I'll give it a name. Oops. I'll call it theta. I might want to have this angle as well. Call it phi. And because this is a right angle, phi will be 90 minus theta. And then hanging from mass A is another object, mass B, which is 35 kilograms. And I guess that's it. So I'm going to draw the free body diagram of each of these right on top of them. So if you remember from the algorithm, we're going to draw a free body diagram for one object. We're going to write down Newton's second law for that object. And then we'll do the same thing for the other object. So I'll start by drawing both free body diagrams, and then we'll do Newton's second law separately. The reason you might want to draw the free body diagrams first is because that's where all of the physics is, and you might want to take some of those comparisons between Newton's third law pairs or expressions about tension, for example, and use them as you're doing this. So what do we have? Well, I have a wire attached to mass A, which is exactly horizontal, so I could call that the force of tension 1A. How about that? Force of tension 1A. And the reason I call it force of tension 1A is because it looks like there are two more wires attached. So there's a force along this wire, which I could call force of tension 2A. And then there's a third wire that's attached, which is this, which I would call force of tension 3A. Let's actually move this guy down just a little bit further. Okay, are there any other forces on this object? Well, we'll go through the list. Nothing's touching it, so there's no normal force. But it does have mass, so there is a gravitational force. So I should also draw another second downward force, which is FGA. So there are four forces acting on that object. Okay, mass B, well, that also has mass, so it should have a force of gravity acting down, so FGB. And you see that it's connected to a wire, so there's going to be a force of tension on it. There's only one tension for that, so I could call it just FTB. And that still allows me to have unique names. Okay, so I have two free body diagrams. One other thing, we were told at the beginning that when we draw a free body diagram, we should indicate the acceleration. Well, this is a special case of acceleration called equilibrium. The objects are not moving, and that zero velocity is maintained, so their accelerations are zero, each of them. So I'm just going to state that off to the side. So acceleration of A is equal to 0, and acceleration of B is equal to 0. And that completes my free body diagram for each of them. It completes the free body diagram, but there's one other piece of information that I could apply here, and that's the rule that we had about tension. So you notice that there's a tension force down on object A, and there's a tension force up on object B, and they act along the same wire. So the rule was if the wire is light, then the tension is the same everywhere along the wire. The magnitude of it is. So I can write that the magnitude of force of tension 3A is equal to the magnitude of force of tension B, the one that's pulling up on B, and then I could give it a simpler name. So because I have T1 and T2, I'll call this T3. So at some point, I'm going to use that equation, so I might make it a boxed equation because it's like an additional piece of information that we have here. Okay, now we're ready to do Newton's second law. So let's start here. So we have object A. Let's just call it MA. And we're going to write down Newton's second law for that object. So we have F net A is equal to MA AA. So that's basically the equation on the equation sheet, but I've just said I'm dealing with object A here. Now we make it specific to the problem, so I have to write the sum of all the force vectors acting. There are 4 of them. So it's ft1a vector plus ft2a vector plus ft3a vector plus fga vector is equal to ma AA. Notice I don't plug in either mg or that T3 thing that I found because those were expressions about magnitudes and these are vectors, so I'm not ready to use that stuff. So we continue. Next step is to choose a coordinate system. We could do that separately for the 2 objects, but I'll probably just use the same one. It looks like just our standard xy would be a good choice because there's lots of vectors that point either horizontally or vertically, so I'll do that. And then we write out one of the component equations. So don't think. It's important not to think here because there's so many subscripts. So if it's true for this vector equation, then I get ft1ax plus ft2ax plus ft3ax plus fgax is equal to ma aax. Okay, it's a mouthful, but you just write it down based on the previous line. And now we do the actual calculation. So remember, up here, this was physics, writing the free body diagram. The rest of it is just vector math. So we now are just doing some math. So going through, what is ft1ax? Well, ft1a is that vector. It points in the negative x direction. So its x component is going to be a negative number, and I can just write it as minus the magnitude. So ft1a. So I've replaced the x component with minus the magnitude of the vector. ft2ax, well, this is ft2a. It's not pointing on the x or the y direction, so I should probably make myself a little triangle for that one, just to see what's going on. So I have ft2a vector, and I'm looking for this number, ft2ax. So that means that I want to look at this triangle. So it has a hypotenuse of ft2a. I'm looking for the x side, and I have an angle in there. I could put phi, but I see now that I actually just have that theta in there already. You see that that's exactly the 53 degrees, so that will make it a little bit easier. So what do I get? Well, x is the opposite, so I get sine of theta is equal to x over ft2a, or x is equal to ft2a sine of theta. So now I plug that in. So, well, first remember, check here, make sure that the ft2ax is a positive number. It is, so it's just this result. So this becomes ft2a magnitude times sine of theta. All right, now we look at ft3a. Well, that's this vector. It points along the y-axis, so its x component is 0. So that will be 0. And fgax, well, it is also in the y direction, so its x component will also be 0. So that becomes 0. And remember, don't stop until you finish out the whole equation. Now I have ma, and then the x component of the acceleration, well, that's particularly easy in this problem because the acceleration is 0. So the whole side becomes 0 there. So my box equation is ft1a vector, ft1a magnitude is equal to ft2a sine of theta. Put a box around it. Now, am I able to solve? Not quite, because I have 2 unknowns here. So we'll continue. And remember, the rule was basically just do Newton's second law until you're done. So let's give ourselves a little bit of space here. Let me move this stuff down. And let's do the y component equation. So the y component equation comes from the vector equation, and we have ft1a y plus ft2ay plus ft3ay plus fgay is equal to maayay. Okay, and now we go through and find them. So ft1ay, well, that was this vector, and it points in the x direction, so its component is 0, y component. To t2ay, well, that was this vector. It has a positive y component. That's going to be this number right here, and that will be found from this side. So that means if this was a sine theta equation, then it will be a cosine theta. So I'm just going to write it. You should probably write it out yourself. It's going to be ft2a times cosine of theta because of this triangle here. ft3ay, well, that one is no longer 0, so it's a vector that points in the negative y direction. So we write it as minus ft3a magnitude. And fgay is again in the y direction, negative y direction, so it's minus fga. The other side has an ay, but a is equal to 0, so that's equal to 0. So our second boxed equation, I don't know what's the best way to write it, but we can write ft3a is equal to ft2a cosine theta minus fga. Okay, second boxed equation. We're not ready to solve it yet, I don't think, because we still have too many unknowns. But we can continue because we have another object. So let's do the second object. So this object here leads us to another version of Newton's second law. So I'll just write it out. F net B is equal to mb AB vector equation. I apply it to the free body diagram I have, which is FTB vector plus FGB vector is equal to MBAB. And then I use my coordinate system. Well, you can see that things only point along the y direction, so I only need to write out the y equation. So that's going to be FTBY plus FGBY, don't think, MBABY. And we get, and then we do the components. So what are the components of this? Well, FTB points in the positive y direction, so it's going to have a y component of just plus the magnitude. FGB points in the negative y direction, so it's going to have minus the magnitude. And AY was equal to 0, so we just plug in a 0 for the right-hand side. So this leads to our third boxed equation, which is FTB is equal to FGB. Now I think we're ready to solve. So let's start with the third equation because I think we can solve that one exactly. Remember, FTB was this magnitude here because it was along the same wire, and it's what we're going to call T3. So the T3 is equal to, and we have an equation for FG, which is MBG. So T3 is equal to 35 kilograms times 9.8 meters per second squared, which is what? Something like 350. Let's plug it in. So 35 times 9.8 is 343 newtons. So there's one. So if we go back and look at our picture, if we're looking for T3, T1, and T2, we found one of them so far. So how can I use that? Well, if I go back to my second equation, that has a T3 in it. So I have T3 is equal to T2 cosine theta minus, and then FGA is MAG, but MAG is just the weight that was given, so that's just the weight of A. And the unknown in this equation is T2. So we get T2 is equal to, well, add the weight to both sides and then divide by cosine theta. So T3 plus the weight of A divided by cosine of theta. So what is that? Plug it in. We have a number for T3. We add it to the weight of object A, which is 175. And then we divide by cosine of the angle that was given, theta, which was 53 degrees, right? Yes. So cosine of 53. And we get 861. So now we found T3 and T2. And finally, we have our first equation, which now can be written as an equation for T1. So that's equal to T2 sine of theta. And we have number for T2 now. T2 is 861. So we take that and we multiply it by sine of 53. And we get 687. So we've solved for everything. So again, notice that I did all this work to get the boxed equations, and once I had the boxed equations, it was very easy to answer all the problems. It looks sort of overwhelming in this picture, doesn't it? But remember, it was exactly the same process that I was doing. Here, 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 all of that was exactly the same thing. So once you start practicing it, it's going to be very easy to just do it over and over again, doing Newton's second law. Well, this has been long already. I think I'm going to hold off and put this last example on its own video. So I'll make a separate video for this last example, but I'll let you go right now on this.